Now I want to move on to t-tests and ANOVA. So this is where we have a continuous outcome variable, but categorical predictor variables. T-tests are a family of tests when we want to compare two means. So for example, if we have a binary predictor, remember that's a predictor that's categorical, but there are only two categories. In a continuous outcome variable, we might use a t-test. We can use an independent samples t-test when our two groups are independent from one another. One example of this is a between subjects experiment, where half of our subjects are randomly assigned to one experimental condition, and the other half of our participants are randomly assigned to a different experimental condition. But it doesn't have to be an experiment. We can also be comparing two independent, naturally occurring groups. For example, we could be comparing parents to non-parents on some continuous outcome variable. That would give us a mean for the parent group and a mean for the non-parent group that we could compare with an independent sample t-test. A special case, a paired or dependent samples t-test, occurs when our two groups are related to one another in some way. For example, in a within subjects experiment, where all of your participants participate in both conditions, we'll want to use a paired sample t-test. That's because the data that go into calculating one mean can be paired with the data that go into calculating the other mean because they come from the same people. Another example when we want to use a paired or dependent t-test is when we have pairs of individuals who are related to one another in some way. For example, romantic couples, a parent and a child, or even just two people that we pair together to interact with one another in the laboratory setting. In that case, the data that goes into the two means are not independent, so we want to use a paired samples t-test. Finally, there's what's called a one sample t-test, and this is when we just have a single sample mean. We don't have two groups, just one sample mean, and we want to compare it to a known or hypothesized population mean. So, for example, we want to know whether our sample mean is significantly different than 0. In that case, we'll use a one sample t-test. ANOVA is what we'll use when we have 3 or more means. So if a t-test is for 2 means, ANOVA is for comparing 3 or more means. But there are different ways that we can end up with 3 or more means. The first way is that we have a single categorical predictor with 3 or more levels or groups. In this case, we use a one-way ANOVA. But we could also have 2 or more categorical predictors. This would also give us more than 3 means, and here we'll use factorial ANOVA. Finally, there's a special case called repeated measures ANOVA that we'll use for a within subject study whenever we have 3 or more groups or 2 or more categorical predictors, also called factors. So in repeated measures, perhaps you'll have the same participants participating over time or participating in 3 or more experimental conditions, for example. Now I want to move on to the right-hand side of this flowchart, this decision tree. We've covered the general linear model on the left, but now I want to talk about the generalized linear model. This is what we can use when we have outcome variables that are not normally distributed, that have some other type of distribution other than that of continuous variables. Sometimes we're interested in predicting outcomes that violate the assumption of normality, and that's where the generalized linear model comes in. One solution is to use what's called a non-parametric test, which is distribution-free. The advantage of this is that they make fewer assumptions, and thus we can apply them to lots of different types of data. However, when our outcomes do follow an expected distribution, and it's just not the normal distribution, we can instead use statistical tests under the generalized linear model, and this is usually preferable because non-parametric tests have lower statistical power. So one example of generalized linear model is a binary logistic regression. This is what we'll use when our outcome variable is binary or has 2 categories. For example, yes, no, presence or absence of disease. Here we're asking whether X, our predictor, predicts the likelihood of Y, our outcome. Another example is Poisson regression, which we'll use for count data when we want to know whether our predictor X predicts the number of our outcome variable Y. For example, number of children, number of doctor visits. Because count data often falls into just a few numbered categories and often is what's called zero inflated, where there will be a lot of zeros in the data, it's typically not normally distributed the same way that a continuous variable might be. And so we want to use the generalized linear model in most instances. Finally, let's talk about non-parametric tests. So again, non-parametric tests are distribution free, meaning they don't make any assumptions about the distribution of the outcome variable. They make fewer assumptions, but they're also less powerful, so oftentimes we want to avoid them if we can. That being said, there are many times where non-parametric tests are ideal, and one common instance where we'll use them is called a chi-square test. A chi-square test is what we'll use when we want to compare the frequencies of two or more categorical variables. So, for example, are parents or non-parents more likely to own pets? Parenthood status is a categorical variable, but so is our outcome variable. People either own or don't own pets. This gives us a table that looks like this, where we have 32 parents that own pets, 54 that don't own pets, 42 non-parents that own pets, and 41 non-parents who don't own pets. To know whether the difference in pet ownership between parents and non-parents is statistically significant, we might use a chi-square test. Now, everything I've showed you so far is using just a single outcome variable. But what do you do when you have more than one outcome variable? Most of the time, you're simply going to predict multiple outcomes in separate models. You'll want to account for the number of significance tests that you're running, but ultimately, you likely won't model them in a single model. There are exceptions to this, and in rare instances, you can use models that allow for multiple outcome variables to be modeled together. Sometimes this is called multivariate statistics. However, people often use multivariate or multivariable to refer to multiple regression, which is where we have two or more predictors. This could be a subfield difference, so you'll just want to be really careful when you're using this term that you're clear about what you mean by it. Lastly, what about other fancy statistics other than the ones covered here? A common one that might come up in developmental sciences is multi-level or hierarchical linear modeling. This is a special type of model that we want to use when our data are nested in some hierarchical manner. For example, we might have observations nested within people when we have repeated measures over time in a longitudinal study, for example. Or we might have people nested within groups, such as students in a classroom. And we need to account for that nesting using multi-level modeling. You might have also heard about factor analysis. This is a tool, a type of model that we'll use, for example, when developing a scale or when validating an existing scale, when we want to know which items hang together and how many different constructs our scale is assessing. You might have also heard of structural equation modeling. This is a really flexible framework that will allow us to test a lot of the different relationships that we've already covered in this video, but will allow for the modeling of latent variables, for example, among other benefits. You might have heard about Bayesian statistics as an alternative to frequentist statistics. This is becoming increasingly popular in many subfields. And finally, there are many more, often field and subfield specific statistical tests than the ones that I could cover in this video. So what do you do with all of these different statistical tests? How can you possibly become an expert in everything I've shown you today, plus all of these other fancy stats? Well, that's where step 4 comes in. Oftentimes you'll need to decide whether you have enough expertise to carry out your analyses or when you need to ask for help. You will not become an expert on every type of statistical test overnight, and you most likely won't ever become an expert in every type of statistical test. Most researchers have expertise in a family of tests that they use most often, and when they have to go outside of that family of tests, they might reach out to collaborators who have more expertise than them. The most important thing is to know enough, to know what you know, and to know what you don't know. Some questions to ask yourself are you confident that you've selected the correct test? Have you used this type of test before? And do you know how to check whether the relevant assumptions have been met, how to run the model, and how to interpret the results? If the answer is yes, you're ready to proceed to step 5. If the answer is no, what can you do? Well, one option is to consult or collaborate. If you're a research assistant, this might mean asking a graduate student, a postdoc, or a PI in your lab for help. Or at any career stage, this might mean reaching out to a colleague or a collaborator who has more expertise with this particular type of statistical test. You might also consult, for example, with a statistical consultant or a biostatistician who can offer you advice, but who doesn't necessarily have content expertise in your research question. Another option is to take additional coursework or a workshop to learn a new type of statistical test. This is a particularly useful option when you know what type of test you need to run, but you're not really familiar with the ins and outs of how to run the model and interpret it appropriately, particularly if this is a type of statistical test you expect to use a lot in your research moving forward. You can also self-teach. As you develop more comfort and expertise with statistics, it's very common to learn a new statistical test by reading about it in a textbook, watching online tutorials. This is a totally valid way to learn new statistical tests, but there are some caveats. And that is that you don't want to get in over your head, and it's always a good idea to consult with an expert the first time that you use a new statistical test to make sure that you're not missing any important nuances. Okay, so once you've chosen an appropriate statistical test, and you've either decided that you can run it yourself or you've found a collaborator who will help you, the last thing you need to do before running your test is checking whether relevant statistical assumptions are met. Most statistical tests make certain assumptions about the data, and if those assumptions are violated, you will get results in most cases, but those results won't be accurate. And that's why it's particularly important to check that these assumptions have been met before trying to interpret your results. To do this, you can read about statistical assumptions that underlie your specific type of model, for example, ANOVA, and how to test whether they have been met. If you find that they haven't been met, there are usually steps that you can take, such as using a different type of test, perhaps using a non-parametric test that has fewer assumptions, or sometimes you can transform your data to get it to meet the assumptions of a given test. Okay, so finally, you've chosen an appropriate statistical test. You've decided either that you have enough expertise to run the analyses yourself, or you found a collaborator who's going to help you run the analyses. You've checked that the data that you have meets the statistical assumptions. Congratulations, it's time to finally run your test. You'll run your statistical test using a statistical software program, most likely, such as R, SPSS, SAS, and Stata, and then interpret your results. The ins and outs of this are beyond the scope of this video, but I'll link some useful resources below.